Just a quick pre-lecture note. I have some good news for you, and that is that given what you've already learned about derivatives plus these two new derivative formulas below, you can probably do way over half of your homework assignment pretty easily right now. Those two formulas are the following. The derivative of e to a power is e to that power multiplied by the derivative of the power. Very straightforward. Secondly, the derivative of the natural logarithm of some expression is the derivative of the expression over the expression, or as I'll show you later, you could also write it as 1 over the expression times the derivative of the expression. But just with those two formulas, you should be able to get well over half your homework done right now. But to get all of your homework done in an efficient way, you will need to remember and use some of the properties of logarithms from pre-calculus. I put those properties and some examples at the end of this video so it doesn't interfere with the flow of the video. But when you begin the part of the video that deals with the derivative of a logarithmic function, that will be section 4.5 material, you could just skip to near the end of the video and go back over those log properties and then come back to it. But if you feel pretty comfortable with those log properties, you won't necessarily need to do that. But at some point, take a look at the very end of this video, which gives you those properties, and make sure you really do remember them. Now let's dive right into the lecture. Earlier we've learned to take derivatives of lots of different types of functions. In this lesson we will turn our attention to exponential functions. We do know that the most convenient base for exponential functions is the irrational number base e. The convenience of this base is primarily because if f of x is equal to e to the x, then it's its own derivative. So the derivative, if f of x is equal to e to the x, then the derivative of f of x is e to the x. That turns out to be a very convenient property, which I've summarized here. In general, if we apply the chain rule to that, we have the formula on the left which says the derivative of e to the u is equal to e to the u times the derivative of u. That's basically the chain rule or the general power rule applied where u is some function of x. In particular, if u is equal to x, we'll get what I mentioned earlier. The derivative of e to the x is just e to the x. So it's a function whose derivative is the function itself. It's a pretty nice property. The examples turn out to be pretty simple because the concept is pretty simple. For example, if I ask you to find the derivative of f of x equals e to the 2x minus 1, find f prime of x, you would simply treat the 2x minus 1 as the u in the formula above on the left. Then you would write the derivatives being e to the u, where u is 2x minus 1, so it would be e to the 2x minus 1, multiplied by the derivative of the exponent. Well, the derivative of 2x minus 1 is just 2. Normally we write the 2 in front, so if you simplify it and write it in the most natural way, you would get f prime of x is equal to 2e to the 2x minus 1. And when you get good at this, you can just realize that you're going to have a multiple of 2 when you start and write the 2 in front and be done with it without all the intermediate steps. So part of your goal is to get good enough at this so that you don't have to show as many steps maybe as I'm showing in these examples. Let's do another one. If y is equal to x times e to the 2x minus 1, find y prime. Well, here you have an exponential, but it's a factor within a product rule. So the first thing you have to do is realize that x is like u in the product rule and e to the 2x minus 1 is like v. So you have a product of two things, one of which happens to be an exponential. But the product rule applies first. So x is like u, e to the 2x minus 1 is like v. The product rule says you take u, which is x, times the derivative of v, which would be the derivative of e to the 2x minus 1, plus, then you reverse it, take v, which is e to the 2x minus 1, multiplied by the derivative of u, which would be the derivative of x. Going back now, you can see as you start, you've got x times the derivative of e to the 2x minus 1. Well, when you get to the derivative of e to the 2x minus 1, you've got to use the rule on the left for derivatives of exponentials. The derivative formula for derivatives of exponentials says you take the exponential written down as it is multiplied by the derivative of the exponent plus, then you've got e to the 2x minus 1 multiplied by the derivative of x. Well, of course, the derivative of x is just 1. Probably want to clean that up a little bit, maybe put the 2 in front of the x. You've got 2x times e to the 2x minus 1, and then of course when you multiply something by 1, it doesn't change it, so that's just plus e to the 2x minus 1. So the actual exponential derivative rule is extremely simple, but as you can see, it can be embedded in a different rule, so they can all be mixed together. So the thing you should be doing always really is just practicing a lot so that it becomes second nature. Let's do another. What if f of x is equal to e to the x divided by x, and we want to find the derivative f prime of x? Well, this time you have an exponential in the numerator, but basically this is a quotient rule. So remember, the quotient rule, the way I think of it, is high over low. So the derivative of high over low is low d high minus high d low over low low, or low squared. So you've got low times the derivative of high minus high times the derivative of low over low squared. Well, low is x. Then you've got to multiply that by the derivative of high. Well, high is e to the x. So that's the derivative of e to the x. Minus, then you reverse it. You take high, which is e to the x, multiplied by the derivative of low. That'd be the derivative of x all over low squared, which would be x squared. Again, remember, the derivative of e to the x is just e to the x. You can see that formula on the right up top where I said the special case is if you get the derivative of e to the x, you just get e to the x because the derivative of x is 1. And of course, when you simplify all that a little bit, you'll end up with x e to the x minus e to the x all over x squared. So you have these exponentials, in this case, embedded in a quotient rule problem. How about this? Find the slope of the tangent line to y is equal to e to the x over 3 at the point 0, 1. We have a picture of what that looks like on the right, but the picture is not really necessary to solving the problem. First thing you do when you look at this is say, well, x over 3 might better be thought of as 1/3 x. When you're taking derivatives, it's easier to take the derivative of a number times x, or a number times x to a power, than thinking of it as a number, as x divided by a number. So anytime I see something like that and I know that I'm going to be taking a derivative, I tend to write x, or x to a power divided by something, is just multiplied by the reciprocal. So dividing by 3 is the same as multiplying by 1/3. So in my mind, it's much easier to think of this function as y is equal to 1/3 x instead of y equal x over 3. Only because I know when I take a derivative of the exponent, it'll be easier, because I can just use the power rule. So thinking ahead to that, I'm now ready to take the derivative. The derivative of e to a power is e to the power times the derivative of the power. So I write down e to the power, which in this case is 1/3 x, multiplied by the derivative of the power, or the derivative of 1/3 x. Well, of course, the derivative of 1/3 x is just 1/3. And most of us write the 1/3 first. It just looks more natural. So I would write that the derivative of y with respect to x is 1/3 times e to the 1/3 x. Now remember what we're doing. We actually want to find the slope of the tangent line at this point. So what we have to do is take the derivative, which represents the slope, but we want to plug in x equal to 0, because the formula says there's an x in the derivative. So you have to take that out and plug in the actual number. So at the point we're interested in, x equals 0, when you plug 0 in, you get 1/3 e to the 1/3 times 0. Well, 1/3 times 0 is 0. Any non-zero number raised to the 0 power is 1. So you're really just doing 1/3 times 1. So the slope is 1/3. This is the same sort of question we could have asked about problems from before we learned about derivatives of exponentials, but now that we do know how to do derivatives of exponentials, we can throw in exponential functions and ask those same questions. So there's very little new in this section. It's mostly just applying our same type of problems with a new type of function tossed into the mix, which means we can also do things implicitly. So you can see this problem where you don't have y equal to, it's not solved for y. It has an exponential component. It has an exponential term. So when you get to the derivative of that exponential, you'll have to use the new rule that we just learned. You know the first step for taking the derivative implicitly is you take the derivative of both sides with respect to x. That means you do it term by term, so you've got to take the derivative of x squared times y minus the derivative of the next term, which is e to the y, minus the derivative of the next term, which is 5, equal to the derivative of 0. Well, the derivative of any number is 0. And now you've got to go back and take the derivative of those three terms on the left. So start off with the derivative of x squared y. That's a product, so we'll be using the product rule. Product rule says take the first factor times the derivative of the second plus the second times the derivative of the first. So that would be first factor x squared times the derivative of y is dy over dx, plus then you take the second factor, which is y, times the derivative of x squared, which is 2x. Now you move to the next term, minus the derivative of e to the y. Well, you've got to go back to your formula. The derivative of e to any power is e to that power times the derivative of the power. So we've got y instead of u, so it becomes e to the y times the derivative of y. Then we move to the third term. The derivative of a number is 0, so the derivative of 5 is 0, and we already have a 0 on the right-hand side. The next step in the, let's move that up a little. The next step in the process of finding dy over dx implicitly is to take the terms that have dy over dx in them and get them on one side and take everything else to the other side. So the two things I've underlined both have dy over dx's in them, so they stay where they are. The one thing that doesn't, that 2xy, goes to the other side and becomes a negative 2xy. Once you get the terms with dy over dx on one side by themselves, then you factor out the dy over dx. So you see there's a dy over dx here and here. If you factor it out, you're left with an x squared in the first term and an e to the y in the second term with that minus sign between them. Once you get to that point, all you do is divide both sides by the factor you want to get rid of on the left. And if you divide both sides by that, you'll get minus 2xy over the quantity x squared minus e to the x. Again, this is pretty much what we've done earlier, except we've allowed for the possibility of a function to be an exponential. This is probably as good a time as any to mention that you really do have to know how to use your calculator well enough for it to help you on these, what's going to turn out to be in a minute, these application problems that we're going to go through. So I want to take just a minute to point out a few things that might be helpful to you. For example, if you press the right combination of buttons on your calculator, you might get something that looks like this. A number with an exponent that might in this case be something like minus 0.04. If you see something like that pop up on your calculator, what does it mean? Basically, it's the calculator's version of scientific notation. Very specifically, the numerical part of the exponent tells you how many decimal places to move. So the decimal right now is sitting just to the right of 5. This is telling us to move the decimal place 4 places, and the sign in front tells us in which direction. If it's a minus, it goes to the left. If it were a plus, it would go to the right. So what this is telling us to do is take the decimal place in front of the 5 and slide it over 4 places to the left, and it's to the left because it's a negative sign. So that 5 to the negative 4 power, what that really means when it's written like that, 5 dot, and then you've got negative 0.04, that means to take the decimal place, and you can see it's been counted over 4 places, and it's going to the left because of the negative sign. If it were a positive 04, it would go 4 places to the right. Simple, but if you don't know what it is, you don't know what to do. So make sure you know how to deal with those. How about this? Have you ever tried to enter a negative number in the Casio FX260? You can't enter it directly. What you have to do is just put the positive value in, and there's a plus minus key on the calculator. You press that, and it inserts the minus sign. So if I wanted to enter -7, I would first enter +7, and then I would hit the key that's got the plus minus on it. And if you do that and look at your calculator display, you'll see immediately that a minus sign pops in front of the 7. You cannot enter a negative sign directly. You have to do it that way. Okay, we're talking about exponential, so the base e obviously comes up, and if you ever want to calculate a power of e, here's how you do it. You enter the power, then you press the shift key followed by that button that's got ln on the face of it and the e to the x above. And you can see it on the actual calculator I've displayed here. Let's see. There's the shift key, and there's the key I'm talking about. It's got ln on the face, and it's got e to the x above. And when you hit shift, it executes the function above the main button. So, for instance, if I wanted to calculate e to the 4th, you'd put the exponent, the power in first, the 4. I always do that first, and then do shift ln. And we're going to talk about ln. It's a natural log, and you've studied it in earlier algebra courses. But the shift part, when you hit shift, it executes the function above the key. So 4 shift ln means 4 on a base of e to the x. And if you did that, you would find out it was about 54.59815,003. And a problem might tell you to round it off to 2 decimal places or 3 or whatever. You do whatever the rounding tells you to do in the problem. Now, if you want to calculate e to a negative power, you have to incorporate the knowledge we have of how to put a negative number in. So what you have to do is put the +4 in, then press plus minus, which puts the minus sign in front of it. So if you look at your calculator at that point, it'll have a -4. And then you do your shift ln, which executes e to that power. And if you do that correctly, you'll get 0.018315638. And in a particular problem, they might tell you to round it off to a certain number of decimal places. But here I'm just showing you how to use the calculator. Simple enough, but it's something that you have to think about, because if you don't, you just look at the calculator, you may have trouble figuring out how to do it. Okay, having done that, let's get back to the problems we're going to work. How about this? The demand function for a product is modeled by A equals 6,000 times e to the 0.07t, where t is in years. Find the rate to 2 decimal places at which the balance is changing when t is equal to 1 year. Well, they ask about the rate. Anytime you have a rate of change, you're going to take a derivative. So you're going to take the derivative of that. If you have a number times the function, the derivative is just a number written down times the derivative of the function. So you just write the 6,000 down and multiply by the derivative of e to the 0.07t. The derivative formula for the exponential says you write the exponential down and then you multiply by the derivative of the exponent. Well, the derivative of 0.07t is just 0.07. If you multiply 0.07 times 6,000, you get 420, so you end up with 420 e to the 0.07t. They want to know the rate at 1 year, so you just plug a 1 in. everywhere there's a t, there happens to just be one t, so you end up with 420 e to the 0.07. Again, this is the skill I've asked you to practice over and over again. I hope you're doing that. So the first thing you want to do is type in the exponent, which is the 0.07. Then you want to do shift ln, which gives you the natural log. And that gives you the answer for this much. But then you want to times it by 420. So you put times 420. And to make it evaluate that product, you have to hit equal to. Same problem now, except t equal 10 years. So we take the same derivative we already found. We don't have to do it over again. But this time plug 10 in. Well, 10 times 0.07 is just 0.07. And to calculate that, it's the exact same calculation as we did earlier, with one exception. We do 0.7 instead of 0.07. So when it's 0.07, you put in that. When it's 0.7, you put in that. Otherwise, it's exactly the same calculation. And when you press equal to and round it to 2 decimal places, you'll get 845.78. So practice these things. Go do these problems as soon as you can while all this is fresh on your mind. Make sure you've got the Casio FX260 so you can practice as you go through here. Using another calculator to do it is a bad idea. You are not allowed any calculator but that on the test. So it's a bad idea to practice with any other calculator. Just a really, truly bad idea. I'm just going to go ahead and put out the derivative rule that you'll be using. The derivative of the natural logarithmic function, and again in calculus we basically use base e. Sounds kind of funny to say it that way, but we typically use base e because it makes our calculus formulas much simpler. So we'll most of the time use natural logarithms because they just make the calculus formulas come out easier. And the first derivative formula stated in terms of natural logarithms says the derivative of the natural log of u is equal to 1 over u times u prime as long as u is greater than 0. Remember, you can't take the log of a negative number or 0. So whatever you take the log of has to be positive. And so this u greater than 0, you don't have to necessarily write it down every time you write this rule down, but you have to keep in mind that you cannot take the derivative, you cannot take the logarithm of 0 or a negative number. They have to be positive. But the basic idea is the derivative of the natural log of something is 1 over that something multiplied by the derivative of that something. Now, most of the time, I like to write that formula slightly differently. And I like to write it this way. If you think of u prime as u prime over 1 and then multiply top times top and bottom times bottom, that formula can turn into something to me that's easier to remember. It's just u prime over u. So the way I like to use this formula most of the time is think of it this way. The derivative of the natural log of u is the derivative of u over u. Both formulations are the same, and if you prefer one over the other, go for whichever one makes the most sense to you. But this is the one that I use most of the time. The exception is if u is really complicated, sometimes I'll write it the first way. But as long as u and the derivative of u are fairly simple, u prime over u is the way I like to think of this. As always, this u is thought of as being a function of x or whatever the variable we're differentiating with respect to. In this case, we are differentiating with respect to x. U is thought of as a function of x. But if u is just x, you can write that formula without the chain rule kicking in. And if you really are taking the natural log of just x, the formula is even simpler. It's just 1 over x because the derivative of x is 1. So if you wrote x prime over x, the derivative of x would be 1 and you just get 1 over x. So if u is a true function of x, you have to think of it like this. If it really is just x, the derivative of natural log of x is 1 over x. Okay, so that's the formula, one of those two variations that we'll be using to do these problems in this section. So, jumping right in, first one is to use the derivative formula to find the derivative of f of x equal the natural log of the quantity 2x squared plus 4. It's not hard to figure out what to do. You're going to think of that 2x squared plus 4 as being the u in the formula, and then you go back to this formula up here and you write u prime over u. Well, u prime is the derivative of 2x squared plus 4, so it's the derivative of 2x plus 4 over 2x squared plus 4. The derivative of 2x squared plus 4 over 2x squared plus 4. Well, the derivative of 2x squared plus 4 is just 4x, so the answer is the derivative is 4x over 2x squared plus 4. See how simple this is? You really don't even need to put that step in there. You can go straight to the answer. The derivative of the natural log of 2x squared plus 4 is the derivative of 2x squared plus 4, which is 4x, over 2x squared plus 4. How about this one? Well, this one has a little complication because you have a natural log of x in it, but the natural log of x is one factor. This is really a product rule problem where x is like the u and the natural log of x is like the v, and when you get to the point where you're taking v prime, that's when this derivative of the natural logarithm formula kicks in. But overall, this is a product rule problem. The product rule problem says you take u times the derivative of v. Well, v is natural log of x, and according to the formula just above, the derivative of the natural log of x is 1 over x. Plus, then you reverse it, you take the v, which is the natural log of x, and multiply it by the derivative of x, and the derivative of x is just 1. And obviously, x times 1 over x is just 1. And 1 times log x is just log x, so you end up with the derivative of 1 plus the natural log of x. This is not difficult, but you do have to have some basic things in your head, and you have to practice to make sure you don't make careless mistakes, or at least to minimize those. How about this? Use the derivative formula to find the derivative of f of x equal natural log of x over x. Well, this is a fraction, so this will be a quotient rule. Low times the derivative of high minus high times the derivative of low over low squared. So that's low, which is x, times the derivative of high, which is natural log of x, minus high, which is natural log of x, times the derivative of low, which is x, and then over low squared, which will be x squared. And of course, the derivative of natural log of x is 1 over x, and the derivative of x is just 1, so you end up with x times 1 over x, which is just 1. And 1 times log x is just log x, so you end up with 1 minus the natural log of x over x squared. Again, you're overall doing a quotient rule, but within that quotient rule, you have to use the derivative of the natural log formula. It's not difficult, but it probably is going to require you to practice a bit to get used to the ideas. Another. What if the function is f of x equal the natural log of the fifth root of the quantity 4 minus 3x? We hit on this earlier when we talked about algebraic manipulation. This is the point that I was making earlier. The calculus will be much easier if you do some algebra on this function first, and you realize from an earlier discussion that a fifth root is the same as a 1/5 power. And then thinking back, you have a formula that says the natural log of x to a power, you can just bring the power down front. Well, that's where the 1/5 comes in. You can take that 1/5 and bring it down front, and you'll end up with 1/5 times the natural log of the quantity 4 minus 3x. Now we're at the point where I was making a point earlier that some people get to the point where they've done all this algebra and say, okay, that's the answer to the question. Just be careful. This is algebra. Those are algebraic manipulations of the original function. We've done no calculus yet. We've used algebra to get it into the form so that we can then do the calculus the derivative. So we're not done. We've just manipulated the function into a form where the calculus will be very easy. So all you do to take the derivative is, we have a formula from a long time ago that a constant times a function has a derivative. You just write the constant down and multiply by the derivative of the function. So by far the easiest way to think about this is just write the 1/5 down and multiply by the derivative of the function of x, which is a natural logarithm. So we just write the 1/5 down and concentrate on taking the derivative of the rest. So we're going to take the derivative of the rest. Well, what is the derivative of natural log of something? Well, that takes you back up to this formula. The derivative of the natural log of u is u prime over u. Well, what is u prime? Write the 1/5 down times u prime. What's the derivative of 4 minus 3x? Well, it's just minus 3 over the u itself, which is the 4 minus 3x. And of course, if you want to clean that up a little bit and write it as one fraction, you can think of taking the 1 times the 1 times the minus 3, and then take the 5 times the denominator. And you end up with minus 3 over the product of 5 and 4 minus 3x. And there you go. Practice makes perfect. Let's do another. This is a log of a fraction. So f of x is the natural log of x over the quantity x squared plus 2. And again, when you recognize the log of a fraction, you're probably going to want to rewrite it as the log of the numerator minus the log of the denominator. It makes the calculus much easier. So that's going to be the log of x minus the natural log of the quantity x squared plus 2. And you can see that's going to make it much easier to find that derivative, because at this point, the first one is just natural log of x, and I know the derivative of natural log of x is 1 over x. And the second one, if you think of the x squared plus 2 as being the u and apply this formula right here, you end up with u prime over u. Well, u prime is 2x over u, which is x squared plus 2, so you get 1 over x minus x squared over the quantity x squared plus 2. You could get a common denominator, simplify it, and write it more compactly, but this is fine. WebAssign's okay with this. I'm okay with this. It's a perfectly legitimate way to write the answer. How about this? Find the derivative of f of x equals x times the natural log of e to the power of x to the 5th. Now that looks horrible, but there's a trick that makes this problem so easy, because this is the natural log of e to a power. Forgetting about the x for a minute in front, the second part is the natural log of e to a power. You've got something that tells you that can be simplified. You've got that property that says the natural log of e to a power is just a power. And anytime you're using the same variable in the formula in the original problem, this problem's got x's and this formula has x's. If it helps you, you can think of the x as being a u. It doesn't matter. You can let the letters be anything you want to. But the point is, the natural log of e to any power, the answer is just the power. Well, this second factor here is the natural log of e to a power. So the answer is the power. But that x is still sitting there. So this x is still sitting there. But this whole natural log, this whole thing that I put in this box is just, according to our algebraic manipulation rules, it's just x to the 5th. Well, that's wonderful. The whole logarithm goes away. So this problem had a logarithm in it and an exponential in it. But because of the way it was set up, the whole natural log and exponential just cancel each other out, and you end up getting rid of the logarithm and the exponential all in one fell swoop, and all you're left with is x times x to the 5th, which we all know is x to the 6th. Again, don't celebrate too early. We haven't done any calculus yet. But we've used algebra to simplify the formula, first of all, but it happens to, in the process, get rid of all the natural logs and exponentials, so you're just back to doing a simple derivative as you learned way long ago. It's just a plain old power rule. If f of x is x to the 6th, the derivative is going to be 6x to the 5th. So that problem that initially looked pretty horrible turned out to be one of the simplest problems we've worked yet. And that comes from knowing your properties of your algebraic properties relating logs and exponentials. Our ultimate goal in this lesson is to talk about derivatives of logarithmic functions, but before we jump into that, it's probably a really good idea to go back and review some log properties from algebra. And the reason for that is that simplifying log functions before differentiating can quite often make the calculus simpler, and in some cases much simpler. So it's definitely worth our time to go back and look at some of those properties that might make the calculus easier. So before we get to our ultimate goal, let's just pause and talk about the algebra of log functions that you've covered in previous courses. We can't reteach the course, but I do want to point out that in any algebra course that you've had as a prereq, you've covered logarithms and you've come up with these properties and you've used them before and you've worked with them before, but you may not be as familiar with them on the top of your mind as you should be. So I just want to go through these very briefly and remind you that you have to bring these back to mind if you want to make the calculus much easier. One of the basic facts is that when you write the log of x base b equal y, that's equivalent to an exponential equation, b to the x equal y. And you spent some time in previous algebra courses with problems that tell you to change from one form to the other. You also came across the irrational number e, which is about 2.71828, similar to pi in that it's irrational and it has an infinite decimal representation, which is why we use a symbol for it. You're also familiar with the fact that you can use that number e as the base of a logarithm. And when we say a logarithm of x base e, we often shorten that to just ln x. So anytime you see ln, you can think of that as a logarithm base e. Extremely useful properties. Get these back in your mind. The log of a product is the sum of the logs. If it's base b, or if it's base e, which uses the ln notation. The log of a fraction is the log of the numerator minus the log of the denominator, again, whether you're using log base b notation or natural log notation, the ln. If you take the log of something to a power, the power can be brought out front. Again, whether you're using the notation log base b, where b could be any positive number base, or if you're using the ln, which is base e. Again, these are very useful in simplifying some of these expressions before differentiating, which makes our life easier, at least the calculus part easier. And I'm going to end this pre-discussion about properties of logs with some just basic facts that if you have them in your head at your disposal, it's going to make your life so much easier. First of which is that the logarithm of 1 is always 0 no matter the base. And again, if that base is e, you could write that same property as ln of 1 is always 0. If the base matches what you're taking the log of, in other words, the log of b base b, it's just 1. And if you translate that into base e, that becomes the natural log of e is always 1. The logarithm of b to the x, base b is just x. In other words, if you're taking the log of an exponential expression and the base of the exponent is the same as the base of the logarithm, you just get the exponent for the answer. And if you translate that into natural log notation, that says natural log of e to the x is equal to x. And remember, x can stand for anything. So the natural log of e to whatever's up there is just whatever's up there. The last couple of really useful formulas. If you take b to the logarithm of x base b, again, the base of the exponent matches the base of the logarithm, you just get what you're taking the log of, which is x. And again, if you translate that to base e, that becomes the property that says e to the natural log of x is always x. please get some of these basic facts back into your head so you can easily access them as you're working some of these problems. Before we get to the calculus, let's practice this a little bit. I'm going to throw those properties back up there so we can look back at them. So I could give you a property like simplify the logarithm of 8 base 2. Well, all these properties have to do with bases matching each other. Well, 8 and 2 don't match each other, but think about it a minute. 8 is really 2 cubed. So if you think of 8 as 2 cubed, that logarithmic expression becomes the log of 2 to the third base 2. Now the bases match, and you have a property that says, I'm actually going to do this 2 different ways, so bear with me. I'm doing it both ways on purpose. Actually, there are 2 reasons I'm doing it 2 ways, but this is the way I chose to do it first. You have a property that says if you're taking the logarithm of something to a power, you can bring the power down front. So that becomes 3 times the log of 2 base 2. And then you have a property that says if you're taking the logarithm of something and that something is the base of the logarithm, you always get 1 for the answer. So the log of 2 base 2, the log of 7 base 7, the log of 50 base 50 will always be 1. So the answer is 3. The reason I put this problem in here is that this type of manipulation can be really useful for some of our derivative problems that we'll do in a few minutes. And it allows us to take this, what I maybe call a strategy, for lack of a better term. If you want to write something, the log of something to a power, you can always bring that power down front. That in itself, right by itself, is a very useful property or strategy that will help us make derivative problems with logarithms easier in a lot of cases. So keep that in mind. Now, I said I was going to work the same problem a second way that's actually faster. I did it this way to show you sometimes there are multiple ways of doing things, but I also did it this way to show you that little aside about it being a useful property for derivatives. But if you actually were just trying to solve this problem in the fastest way you could, if you still think of the 8 as 2 cubed, we have a property that says if you're taking the log of something to a power and the base of the exponent matches the base of the logarithm, you just get the exponent for the answer, and so you get 3 immediately if you use that property. You can see it works either way. And that happens in a lot of cases, that sometimes you can get to the same result in different ways. The first way is a really useful strategy for us later on doing derivatives. The second way is actually the fastest way to answer this particular problem. And keep in mind, the natural logarithm is just a log with base e. So anything we say about base b also applies to natural logarithms because e is just a particular b. How about this? Simplify the natural log of e to the third. Again, we have a property that says when you're taking the natural log of e to a power, the answer is just the power. How about this one? Simplify the natural log of the fifth root of e. Well, we don't have any properties that deal with radicals, but we can think of the radical as a fractional exponent. We've been doing that. So if you think of that the fifth root of e as e to the 1/5, now the property that says the natural log of e to the x is x applies, and you can see that the answer is just 1/5. It would benefit you a lot to go back and think about these and make sure you have them in your head before you start the calculus material that we'll get to shortly. How about this? Write the log of x times the square root of x minus 1 base 2 as a sum. If you look back, there's a formula involving a sum, and it says if you take the log of a product, you get a sum. So if you take the log of x times the square root of x minus 1, you can write that as the log of the first factor, which is the x, plus the log of the second factor, which is the square root of x minus 1. How about this? The log of a fraction, x over the square root of x minus 1 base 2. Well, you have a property that gives you that as well. If you have the log of a fraction, you can write it as a difference. The log of the top minus the log of the bottom. Evaluate log of 16 base 2 without a calculator. Well, again, we have properties that tell us how to simplify some of these things if the bases match. Well, 2 and 16 don't match each other, but similar to the 8 that we did a minute ago, 16 is a power of 2. If you think of 16 as 2 to the 4th, now the bases do match, and you can use the property that says you can bring down the 4. You could have also done it by the other property that says if the bases match, you get the exponent for the answer. Either way, you get the same thing. How about this? Evaluate 1 over 27 base 3 without a calculator. Well, that's the log of a fraction. So you're probably going to suspect that, well, I could write it as a difference, and you could. There's actually a simpler way. 27 and 3 are not the same, but 27 is 3 cubed. So what if I wrote that as the log of 1 over 3 cubed base 3, and then change that 3 to the third to 3 to the minus 3 by pushing it up to the numerator, and that would change this whole thing into the logarithm of 3 to the negative 3 base 3, and now the exponents match up. Now the bases match up, and you get the exponent for the answer, so the answer will be negative 3. Go back and practice these and look at them, write them down, see if you can work them out and make sure you understand them. You can come back here and confirm that you're doing them right, and get these back into your head. These properties will help you with the calculus. Sometimes students get confused and they do all this algebraic manipulation to something, and they forget that they have not done any calculus yet, and they just stop. But if there's a calculus problem, you have to do a derivative, something like that, and you've only done the algebraic manipulations, you're not through. You've just gotten the problem into a shape so that you can do the calculus. So be careful when you're doing these problems to not think you're done when you've just done the algebraic manipulation that allows you to do the calculus.